what really should be going on.
Since a digital image is sampled at discrete locations in space, it can be written down as a two-dimensional array or matrix of values. Here is an example. Note that this matrix has fractional values, both positive as well as negative. But what if we could only represent a small set of integer values, say between 0 and 5? How would you quantize this matrix so that the result consists of only the integers 0 through 5? Enter the converted values in the corresponding boxes. Assume that we always round down. For example, 1.8 becomes 1. Also, be careful about the limits. Anything less than the lower limit, 0, should be converted to 0, and anything greater than the upper limit, 5, should be converted to 5. To get the quantized matrix, convert each number, always rounding down. Integer values within the given range remain the same. Anything above the upper limit becomes 5. Similarly, anything that is less than 0, in this case minus 1.3, becomes 0, and so on. Note how quantization results in a loss of detail. Extreme values beyond the range are lost as well. Alright, let's try to load and display an image. To load an image, we want to use the imread command. The image will be stored in this variable img. To display it, we want to use the imshow command. Hit test run and scroll down to view the output. A bottlenose dolphin surfing the waves. Alright, what more can we find out about this image? What if we wanted to find out the size of the image? You guessed it, we'll use the size function. That returns the size of the image. To display it, we'll use the disp function. We can also find out the class or data type for the image. Go ahead and type out these commands, run the program, and note down the results. So what was the size of the image? Note that Octave prints out the height first and then the width. What was the class or data type of the image? Type in your answers. Alright, let's find out the size and class. Octave prints out the height of the image first and then the width. Height is 320 and width is 500. On the next line, we see that the class of the image is uint8. If you type these values in correctly, good job. So the height and width turned out to be 320 and 500 respectively. And the class was uint8. Now what does uint8 mean? Some of you may know this already. U stands for unsigned, which means this data type cannot represent negative numbers. Int stands for integer, and 8 refers to 8 bits, or 1 byte. This is sometimes known as the bit depth. It indicates the number of bits allocated to store each intensity value. Let's look at some values from our dolphin image. As before, we load the image with imread, and let's also display the image with imshow. How about we print out the size as well? And let's run this to make sure everything's okay. Alright, dolphin's still there, and the size is still 320 by 500. Let's say we want to find out the image value at a particular location. We specify this location with a row and column number. We learned earlier that an image is a function over the two dimensions. Octave uses a notation similar to a function to access values at a particular location. Let's say we want to find out the value at row 50, column 100. We'll write img, that's our image variable, followed by the row column coordinates in parentheses. And let's display this value. Alright, let's see what we have. So the value at 50, 100 is 208. Similarly, we can find out the values for an entire row. We'll use a similar notation as before, but we'll do something different for the column. Putting a colon tells Octave to return values for all columns. Let's see what the output is. As you can see, Octave dumps values from the entire row, all 500 columns. Obviously, this isn't a useful way to look at values from an entire row. What else can we do? We can plot these values. This makes more sense, doesn't it? You can clearly see the relatively higher values where the white wave is, and then the other values are comparatively low. Can you find out the values from this 3 by 3 slice of the image? Rows 101 to 103, columns 201 through 203. Fill in the values in the corresponding boxes. Alright, to select the desired slice, we specify a range of rows and a range of columns. In this case, the range of rows is 101 through 103, and the range of columns 201 through 203. And let's display these values. So the numbers are 81, 77, 77, 81, 78, and so on. Let's use this method of selecting a range of rows and columns to extract a larger portion from an image. By the way, this is also known as cropping an image. Let's use a different picture this time. Let's see what it looks like. Alright, a classic two-wheeler there. Let's check the size of the image first. Alright, 320 by 500. When cropping this image, we'd want our limits to be within this range. Let's say we want to select rows 110 through 310 and columns 10 through 160. I wonder what we'll find there. That's the front wheel. No points for that. So what is the size of the cropped image? As before, let's use the size function. So it turns out to be 201 cross 151. Is that surprising? Why isn't it 200 cross 150? Let's look back at the range we selected. 110 through 310 and 10 through 160. Note that in both these ranges, the limits are inclusive, which is why the first range, 110 through 310, includes 201 different rows. Similarly, 10 through 160 includes 151 different columns. Try to extract different parts of the image. What happens when your selected range goes out of bounds? How about we look at a color image? What do you think is the size of this image? Let's find out. 258, 320, and 3? Why are there 3 numbers? The first two are the height and width. The third one is the number of color planes or channels in the image, which is 3. So how would you select a single color plane? We'll use the same indexing notation we used to crop an image. Say we want to select the red channel, which is at index 1. We want all the rows, all the columns, but only the first plane. Now what does this look like? Alright, so that's what the red channel looks like. Brighter areas indicate higher red values and darker areas vice versa. The apples are not as bright as you'd expect. Why do you think that is? Let's also figure out the size of this color channel. As expected, the width and height of the color channel are the same as the original image, but it doesn't have a third dimension. Well, that makes sense, doesn't it? This color plane is one of 3 which are stacked together to create the color image. Each one of them is a 2-dimensional array. Note that the extracted color channel is an image by itself, so you can apply the same operations as you've seen before. Let's try plotting the values from a row of the image. And that's what the plot looks like. Play with this image in the code editor. Try out different operations. Try selecting other color channels. So what do arithmetic operations on images look like? Let's start by adding 2 images. Like before, we load up the images. Let's display them and make sure their sizes are equal. Here are the images, and as we can see in the program output, their sizes are equal. This is important because addition is an element-by-element operation. This means pixels in one image get added with corresponding pixels in the other image, and so on. Since the 2 images are of the same size, we can add them. Octave is intelligent enough to figure out that these 2 are matrices of the same size and hence performs an element-wise addition. The result is, as you would expect, an image that has elements of both source images. You can clearly see the bicycle and the white surf. You can also see the dolphin faintly visible. Notice how this image is exceptionally bright. Many areas are washed out. Why do you think the image is so bright? To find out, let's look back at our code. Note that we are directly adding values from both images. Areas where both images are bright turn out to be doubly bright. This indicates that we should perhaps scale down the image intensity values. By how much? Well, think of a pixel where both these images have the maximum intensity value. That pixel in the summed image will have twice the maximum value. So if we want the maximum possible value in the summed image to be the same as the maximum possible value in each of these source images, then we want to divide the intensities by 2. Does this look familiar? Yes, this is the average of the two images. Let's see what this looks like. Alright, much better. Compare this with the direct sum. You can clearly see the difference in brightness. Also notice that there are no longer any washed out areas. Let's rewrite the expression for average and see what happens. Since both bicycle and dolphin are being divided by 2, we should be able to add them first and divide the result by 2, right? And let's call it average alt. Let's see what this looks like. Wait a second, this is not right. Shouldn't the two results be the same? To understand the result we are seeing, let's take a closer look at the computation that is happening behind the scenes. Here are the two images. The first image is the result of dividing each image by 2 and then adding them. And the second is the result of adding the two images first and then dividing by 2. The first image has better detail and is also slightly brighter than the second one. Now we know that these images are just collections of intensity values, and values at each corresponding location are being added together. Let's take two sample values, say 183 from one image and 152 from the other. Now in the first case, we divide these numbers by 2 and then add the results. In the second case, we add the two numbers first. What do you think is the result in these two cases? The key to solving this problem is to know that both these images are of type uint8. This means that all pixel values are integers in the range 0 to 255. So here's what happens. Since the images are unsigned integers, Octave tries to retain the same data type throughout the arithmetic operation. So 183 by 2 comes out to be 92. Note that Octave rounds to the nearest integer. In this case, it is rounding up. Similarly, 152 by 2 is 76, and their sum comes out to be 168. In the second case, the addition is performed first, so 183 plus 152 is 335. But note that this number cannot fit in the unsigned int 8-bit range. The maximum value possible is 255, so this number gets truncated to the upper limit. The division proceeds as expected, and the result is 128. You can imagine that in a number of places, the pixel values add up to more than 255. In all these locations, you will only get 128 as the result. This is often less than the actual average of the two numbers. Hence, we see that the first method better preserves pixel values. You will certainly come across these odd arithmetic errors. Just be mindful of the image data type you're using and the order in which you perform arithmetic operations. In the previous example, we saw how we can divide an image by a number. Dividing by 2 is the same as multiplying by 0.5. And the order of writing these two doesn't matter either. The constant 0.5 is known as a scalar. This potentially comes from the fact that it scales the image values. Let's see what the result looks like compared to the original image. Half the intensity values, clearly darker. Note that we can potentially multiply by any number, even greater than 1. Multiplying the intensity values by 1.5 makes the image brighter, and we see the same washed out effect in certain areas. This is due to the image values above 255 getting truncated at that limit. In Octave, we can write a function to perform a common operation. Let's turn the scaling into a function.